Activity 14.4 is the princess's dilemma. And this is going to be an example of a simulation that we're going to do based on this story. So, once upon a time, there was a powerful king who wanted his daughter, Princess Cecilia, to marry a wealthy man with royal blood. With this in mind, he arranged a wedding with the neighboring king's son, Prince Roland. At first, Princess Celia did not seem opposed to the arranged marriage. However, as fate would have it, she met a young man in the village and fell in love with him. Princess Cecilia pleaded with her father to cancel the arranged marriage so that she could marry Merthin, the man she loved, the man she met in the village. At first, the king was furious. He wanted to throw Merthin to a pack of wolves. It took many hours of his beloved daughter's begging to convince him to allow the following compromise. The king demanded that Merthin enter the maze, which led to two rooms. In one would be Princess Cecilia, and the other would be the wolves, hungry wolves. So we have a map of the maze and the rooms. Okay, so study this map a little bit and figure out Princess Cecilia gets to choose which room she goes and waits in, and the other room will have the wolves. So would you wait in the green room, which is room one, and or the red room, which is room two? The maze starts at point A, so he has a choice of going left, straight, or right, and then at point B, C, and D, he can go left or right. Okay, pick a room. And now we're going to simulate this. We don't want to actually do this and have him eaten by wolves. So to simulate the fate, we can roll a die at point A. And then if it lands on one or two, he goes left to point B. If it lands on three or four, he goes straight into room two. If it lands on five or six, it's going to go right and he gets to point C. If he gets to B or C, he's going to flip a coin. And let's see, if heads, he goes left. If it's tails, he goes right. So let me do one of these. I rolled a 5. That means I'm going to go to point C where I'm going to flip a coin and I get heads. And it said heads goes left. So I get to point D where I have to flip again. I get tails, I go right, and I end up in room 1. We're going to perform this experiment 20 times. And I just ended up in room 1. You just put an X in room 1. I'm going to show you the virtual version of this, the app, or you can play it if you have a die and a coin. Okay, so this is the app, and you'll see the same story, the princess's dilemma. So here's the maze. I'm going to roll a die. Get to point. After that, I'm going to flip a coin and I end up in room 1. So this is the whole path, but for trial 1, you end up in room 1. So this is 10 trials. You can go ahead and do it twice. So you actually have data on your sheet for 20 trials. So you've done this trial now 20 times. This entire table should be filled out. Based on your table, add up how many times you end up in room 1, how many times you end up in room 2, and based on your table, decide which room that Cecilia should go wait in. So the room he ends up more in your simulation. Now we're going to look at the theoretical probability. So if you remember at point A, we were rolling a die, right? Die has 6 sides, and a 1 or 2 went left, a 3 or 4 went straight, and a 5 or 6 went right. So what is the probability? Well, if it's out of 6, this is 1/6 plus 1/6, which is 2/6, which is 1/3. That means this will also be 1/3, and this will be 1/3. When you got to B, C, or D, you flipped a coin. It was heads or tails. And heads or tails is 1/2, 1/2. So what we've done now is we've put weights on the branches. If you have different probabilities, then the branches can have different weights. So if you get into room 1, A to B, and you go left and left, the first left has a probability of 1/3, and then you had heads, which is 1/2, which will be 1/3 times 1/2, which is 1/6. So if you go left and right, then you go left, right, which is 1/3 times 1/2, which is also 1/6. Room 2 just means you went straight, which was a probability of 1/3. To get to room 2, you went right, then left, then left. This is 1/3 times 1/2 times 1/2, which is 1/12. Here you went right, left, right, which is 1/3 times 1/2 times 1/2, again, which is 1/12. So it went right, then left, then right. The probability weight of those branches is 1/3, 1/2, 1/2. That's a 1/3 times 1/2, 1/2. And here you went right and then right, which is 1/3 times 1/2, which is 1/6. So if you look at these different outcomes to end up in these different rooms, you have different probabilities. Room 1, you get there from going left and left, and that's a probability of 1/6. But the room 1 down here is right, left, right, which is a probability of 1/12. The room 1 down here is right, then right, which is 1/6 again. So there are 3 different ways you can end up in room 1. You either go left, left, you go right, left, right, or you go right, right. In order to get to room 2, you have these 3 paths. You either go left, right, which was a probability of 1/6. You go straight, which is 1/3, or they went right, left, left, which is 1/12 again. So you can see that you no longer have equal probabilities at the end of these branches. If you think back of the first probability tree we looked at with the flipping of a coin 3 times, we had 8 outcomes, and each of those outcomes was equally likely, so it was 1/8 for each of them. Not the case here because we have weighted branches. Okay, the fact that we multiply has a name. Multiplication rule for a tree diagram is that a multi-stage experiment, that just means you do more than one thing. You toss 2 coins, roll a pair of dice, or you roll a die and then you flip a coin. That's multi-stage. You will multiply the probabilities along those branches. So in room 1, I highlighted in green. So he either went left, left, or he went right, left, right, or he did right, right. And the probabilities of those were 1/6 plus 1/12 plus 1/6. Get a common denominator. So 2/12 plus 1/12 plus 2/12 is 5/12. Go to room 2 on the previous page. I could go left, right, or straight. I guess I didn't have a letter for that, but straight, or you went right, left, left. Left, right was 1/6. Straight was 1/3, and right, left, left was 1/12. Get a common denominator. Since there was only room 1 and room 2, ending up in room 2 is the complement of room 1. So you could have done 1 minus 5/12. That also would have given you 7/12. We just did it the long way. So where should she weight based on the theoretical probability? Well, she should weight in room 2. If we do percents again, let me find my calculator. It's always easier. So this is my 41.6%. chance. And this is a 58.3% chance. Room 2. So he has a 7 out of 12, or a 58.3% chance of ending up in room 2. Even if Princess Cecilia waits in the best room, is it still possible Merlin will be eaten by wolves? Explain. And I will leave that one for you.